Okay, good afternoon. Welcome to this special colloquium of ICTS, and it's also part of the ongoing program that celebrates this very exciting results coming from DESI. Today's speaker is Shadab Alam, who is a cosmologist at TIFR. He works on a wide aspects of cosmology, but primarily focusing on large-scale structure, including its implication in dark matter and dark energy, etc. And he's also part of the DESI collaboration, which has put out these very exciting results recently. And today we will hear from Shadab those excitement.
So thanks a lot for hosting us, and thanks a lot for coming on such a short notice. I'm going to talk about cosmological results, especially focusing on dark energy from DESI. And then some of the things I'll be talking about you have already heard in the morning, but since there's a little bit of larger audience, I'd like to repeat some of the things, but hopefully there will be not too much of repeat. But more importantly, actually what you have heard and seen since this morning, you have already seen all the results and all the aspects of the analysis. What I really would like to try to do is to construct the physical picture and walking you through all the different steps of this, and give you a feeling of why we do certain kind of things. There are sort of certain things we have told you is done in this way. There are this kind of galaxies. I'll try to give you some impression of why we look at certain specific kind of things. Right, so let's start by, so let's start by, first of all, I'd like to thank our sponsor. DESI collaboration have a diverse set of sponsors starting from DOE, and there are about 72 participating institutions. So let's start thinking about what are we trying to do, as this talk is mostly focusing on cosmology. We start by homogeneous and isotropic universe. There's still a small question mark, and we're still trying to understand whether it's really completely homogeneous and isotropic. But once you start with that assumption, now you can start about thinking that we are living in an expanding universe. So expanding universe is generally illustrated like this. And then one of the important thing here is the scale factor, which is essentially scaling of the universe at time progress. We said in our convention, A of 1 is equals to today, which means A is equals to 1 is redshift 0 today, where we are. Now, if you want to sort of set up this kind of universe, you start by looking at Einstein field equation, and then from there on, you want to think about FLRW metric, which already have all these assumptions about homogeneous and isotropic. That's the framework we are looking at. So this is how you can write down the metric of the universe. And then one of the most important thing to first order when people thought about this framework is to characterize what is the rate of change of A. So that is parameterized, particularly A dot over A is Hubble constant, but really what we are really after is A dot. So what is the rate of change of A? And if you want to sort of work that out, given these assumptions and this metric, what you will end up getting is essentially how does A evolve as a function of different ingredients of the universe, what is the total matter density, if there is an additional term, how does that affect, and what are the different ingredients to it. And as you can see in the true Friedmann equations, there is A dot and A double dot. So you're talking about rate of change, and you're talking about if there is acceleration or deceleration of the universe. And so these are sort of the three things you want to think about, and that is really the picture we are trying to draw. So we're trying to really find out fundamentally what is this A in a great detail, because that helps you figure out what are the different ingredients of the universe and what are the physics of these ingredients. How do they act overall when you look at the very last case. Now, given that picture, now you might want to think about, okay, if I think about overall expansion of the universe in this picture, if I have different kind of components, for example, if I have matters, if I have matter, or if I have radiation, if I have some special kind of component, how does the density of these things evolve as the universe is expanding, in this picture? So here the x-axis is a scale factor, which I just introduced, y-axis is density of different things, and if somehow you can set the initial condition, and this initial condition is set by cosmic microwave background measurement already. So we do have measurement of this initial condition, but let's say, I don't want to go into detail of that, but let's say once you know the initial condition, what is the initial density, initial content of the radiation in the universe, what is the matter content of the universe, then you can very easily see how those things evolve essentially by looking at this equation. Right, so the density evolves at For a normal matter, it essentially evolves at cube root of volume because everything is conserved. So all you're saying is that volume is increasing, and so the density is going to go down. And that's basically shown is this blue line. Radiation goes as a to the minus 4 because apart from the volume is increasing, the radiation itself is getting stretched, and so the energy density of photon or the lambda gets changed by another scale factor, and so that gives you a to the minus 4. Now, there's this interesting mysterious component, which is what we call cosmological constant, where we are saying that W is equals to -1 for cosmological constant, which means energy density of this component, which we are still trying to understand, is constant. So it stays a constant all across the universe. So given these three components, what you're going to realize is that, and given how the initial condition is set up, that there was an era where radiation was the dominant term in the universe. Then that transition led to a matter-dominant region, and now we are just entering dark energy dominated region or cosmological constant dominated region. And so these have huge implications in terms of what the universe, how the universe is going to evolve. Now, given that now that you have an idea of that, we are thinking about expanding universe, you're thinking about its rate, and you're thinking about its acceleration, deceleration, and overall, the energy density of various different components is what is driving this thing. This is where the proposal of dark energy came in, that there is observations showing that universe is accelerating rather than decelerating or just going on with constant velocity. And then when we have done precise measurement of this, I already showed you the value of that. What we found is that roughly 70% of the content of the universe is in this form, which is causing this acceleration. So if you want to sort of characterize this mysterious component, which I said cosmological constant, but you want to think generally, right? It doesn't have to be cosmological constant. And one of the things we want to understand is it really cosmological constant? So for cosmological constant, I said W is equals to -1. Dark energy equation of state, when it's set to -1, the energy density is constant all across the time. But if you define W generally as the ratio of pressure to density, W can be in general function of redshift. And this is one of the interesting quantity we want to measure. If you write any microscopic theory to explain this sort of phenomena, most of these microscopic theory will predict some form of W. But what I'm trying to tell you right now is that let's generally think about what are the different physical scenarios, and then you can relate it to different microscopic picture. Right. So depending on what is the value of these things, it can be cosmological constant for W equals to -1. It can be modified gravity. It can be, there are extra dimension in string theory, which proposes this sort of accelerated expansion. There can be multiple scalar field in the universe, again, that can cause that will give you certain specific functional form for dark energy equation of state. Right, so now, given that framework, let me try to draw this picture of A itself and A double dot, which is trying to look at the acceleration, deceleration. And you'll notice that I'm going to show you both past and future. Future is something we can never observe, but for the illustration purpose, it helps you to see how the future looks like. Otherwise, it's harder to see what the differences are. So if you are in a universe which is just matter only, there's no additional extra component, the scale factor will look something like this, and these are all already set to our best values of cosmological parameter. All the parameters are fixed here. And if you look at the A dot, which is the double derivative of A, what you're going to find is that A dot is negative at some region, and these are all matter-dominated region. And then slowly it approaches 0. The reason it approaches 0 is that as the universe is expanding, the gravitational effect of matter in terms of causing deceleration becomes weaker and weaker, and at some point you just start to go on with some constant rate, right? So that's why A double dot goes to 0. If you add cosmological constant, so this is the lambda CD model, what we have talked about, then it causes accelerated expansion. And since we just entered this accelerated expansion region, if you look at today, then we are in this plot, you can't even see the difference. If I'll zoom in, then you'll see some of the difference. But you'll see in the future, there will be remarkable difference compared to matter-only universe. Now, if you say, okay, let's think about the scenario where W is not -1 but -0.5. So this is the scenario which is also described by quintessence model, where dark energy equation of state not entirely constant, but it's such that it's not as strong as lambda CDM, but it's slightly stronger than the CDM scenario. But in this case, what happens is that since dark energy equation of state is decaying, ultimately you approach somewhat very small acceleration. So rather than this keep going on in terms of the large acceleration. If you set W to some value which is less than -1, and -1 is always an important quantity because that gives you cosmological constant, then the accelerated expansion is even faster, and then acceleration also just increases even much faster. And so this is a scenario where we say it's a phantom or big rip, because that just means somehow the universe is creating more and more energy in this phase of the universe. And there can be scenario which is actually what I'm labeling it is beyond single field dark energy, where dark energy equation of state is self-changing, and it changes such a way that it crosses -1 and it approaches 0 as you go to redshift 0. And so in this case, I'm showing this red line where you see it's very close to the CDM scenario. And then the red line, if you look at in terms of the A dot, it just went into the accelerated expansion of the universe very recently. And then if you look at redshift 0 today, its acceleration is 0, and then it's going to decelerate at some point and then finally saturate at 0. So this is a very interesting scenario. So far, we haven't been looking at this in much detail prior to DESI result. One interesting thing, implication of this scenario is that there is a theorem called no-go theorem, which is basically states that in any of these single field model, you cannot cross W of -1. So you can either be above or below -1, but you cannot cross W of -1 because that's when you start to see singularities, sound speed will blow up and things like that is going to happen. And so for that kind of model, you need at least 2 additional fields. So one field is not going to be enough. So this is why I labeled it to beyond single field dark energy.
But one of them will still be phantom light?
One of them will still be phantom light, and then you have to sort of fine-tune them to make sure to get exactly this energy. So one of them will still be phantom light, other one will be in the quintessence region. So the last line I showed you, red line, is actually uses the best fit values from the Dark Energy Survey, and this is the result. So without going into how we obtain this result, I just want to quickly flash. This is Dark Energy Equation of State measured by DESI survey plus combined with cosmic microwave background, and this is the overall evolution. This is a 2.6 sigma deviation from a lambda CDM scenario in terms of quantification. If you look at the evidence, it's a similar level of evidence is what we see, about 2.6 sigma if you do evidence calculation. If you combine this measurement with supernova, then you can get, depending on what kind of supernova sample you combine with, whether Pantheon Plus, Union 3, or DES supernova year, 5-year supernova, you get some slightly different constraining power. And then there are some issues within the supernova itself, and so which is part of the reason why from the DESI collaboration we are quoting our headline number is this, and these are just bonus point what's going to happen if you're curious, but this is something we need to dig into a little bit more deeper. And so if this is true, if this turns out to be at large significance, let's say in upcoming data set, if we find this to be like at 5 sigma, then this will have huge implication, as I told you. This already will rule out any sort of, if dark energy equation state is crossing -1, then that's a big problem. And now you need to introduce at least 2 fields to explain whatever the macroscopic picture you want to build in for this dark energy. What is? K-sense. Yeah, so similar to quintessence, there are these models which are called kinetic essence model, which have a negative kinetic term. And then that can be either in the W less than -1 or W greater than -1, but it cannot cross -1. Same issue will be there. Yeah, K-sense is also single. Yeah. What is 1 minus A? Yeah, so I'm showing you a plot of W of Z, but the W of Z is fit through a parametric model. And the parametric model is this. So what I'm saying is that W of Z is a constant plus 1 minus A, we raise the scale factor, times another constant. And so this W naught and W is actually what we are fitting. So we are assuming this particular form. You could do this reconstruction without assuming this particular form, and there are papers on that. You roughly get the same thing but slightly different significance.
Shadab, sorry, just a silly question. Why are the bars smaller for when you combine with all these others compared to the the first plot? Like the width of that shaded region.
Right.
Why is it going down?
So this width of shaded region is our confidence. What we're trying to say is that this is our best fit, the solid line, and this is 1 sigma region.
Correct. Yeah.
And so when you combine, this is just DESI plus CMB. When you combine more data, you naturally expect the error to reduce, right? And so when you combine supernova, your error reduces, and so our 1 sigma.
So, but shouldn't you, I mean, these are errors for different experiments, right? I mean, how can you combine the errors in something? I mean,
no, so what happens
the
is,
error would reduce if I would do it in the same experiment, no? Sorry if I'm very
not necessarily. So what we are talking about is trying to constrain dark energy equation of state. Now, dark energy equation of state is sensitive to several things. And so if I, let's say, measure 2 different things, both are sensitive to dark energy equation of state, I can introduce common parameter, and then I can have a common error on the overall thing. And that common error will be smaller than any individual error. So it's just that the same physics is affecting 2 different measurements, and so you can combine them and constrain them. But you have to be very careful before doing that. You have to make sure these are consistent in many different ways. There is no inconsistency which can cause issues.
Okay, and just another, why is it at the lowest redshift? I mean, the least error in your first plot, the least error is somewhere at z equal to 0.5, right? I mean, least confidence, I mean, most confidence. Why is that? Why is it, so the nearby ones are much more uncertain, the z equal to 0 ones?
Right. So what happens is that all of these experiments, I'll show some of that aspect later, is a redshift dependence, which means your measurements are at various different redshift, and so your constraints are at various different redshift. Now, at different redshift, there are different things which is dominating the error bar. So this is something I'll talk about in a bit more detail later on. So if you don't mind, I'll come back to that later. Hopefully, it will be clear by my slide 15 or so.
Can I just ask?
Yeah.
Is there any model at all which is unitary and which gives W less than minus 1, which doesn't have this problem of negative kinetic term for the scalars?
I haven't. I'm not aware of any such model. So any times you go W minus 1, as far as I know, you always have this ghost problem or
non-unitary model.
Yeah, non-unitary model. Actually, in terms of the number of objects, we have much higher number at small redshift. What is, since we all know, this is basically cosmic variance limited. At lower redshift, when you see the universe, you're seeing it essentially in a spherical shell. So at lower redshift, your volume is much smaller, and all of these errors scale with volume. So when you have larger volume, you have better error. But then in that case, you should have a smaller error at high redshift, but then there are other things at play. For example, dark energy equation of state itself is not very relevant. The sensitivity is much less to our measurement at the scale, because here we are matter dominated. Dark energy is just really starting to play a big role starting somewhere here. And then fact that it's harder to see objects at higher redshift. Right, so okay, I've already showed you result, and I've sort of drawn the big physical picture, but let me try to take you through a little bit of connection about how do you sort of go about measuring these things. How do you go about measuring dark energy equation of states? As I started talking about expanding universe, right? So if we can measure scale factor as a function of time, precisely, you can measure a lot of things, including curvature, neutrino mass, and dark energy equation of state, because all of these things is going to affect exactly how A is evolving. Now, if you want to measure E of t, there are basically 2 things. You need to measure scale factor, and you need to measure time at various different scales. So let me tell you how we measure scale factor for different galaxies, and that is basically through a spectroscopy. So if you do a spectroscopy, as we know, the light is consistent of various different wavelengths. In optical wavelength, this can be essentially analogous to color, different color and different wavelength. So when a light is emitted from various galaxies, these lights, as it travels through the space, it gets expanded. You're going through the expanding universe, and so the wavelength gets stretched. And so that is really the effect of dark energy. There are many more effects which happens, things like peculiar velocity, gravitational redshift, all of that is going to affect this stretching of light. All of that I'm ignoring for the purpose of this talk, but I'm happy to comment on those details. And so what happens is if you are going to measure a spectra of a galaxy, you'll see some feature like this. For example, this one is O2 doublet, but plotted in such a way that it's merged and you only see a single line. You'll see this fingerprint of this galaxy at certain wavelength. And then if you look at a galaxy at some other wavelength, you'll see that this fingerprint is at different wavelength. So this shift in wavelength is what we call, we can measure delta lambda. So we can measure this for individual galaxy if you have a spectra of galaxy. And that essentially allows you to measure scale factor of the universe for that particular galaxy. So if you measure redshift, which is delta lambda over lambda emission, and lambda emission we know from the basic quantum mechanics what are the processes which is generating these lines. So we already know the locations of these lines which should be observed in the local universe. We can measure this redshift, and redshift is connected by scale to the scale factor as 1 over 1 plus z. So, so for individual galaxy, we can measure their scale factor or redshift, but you cannot measure time of emission. So that's the other axis. If you have two axes, then you have A of t. But unfortunately, there's these galaxies are not tagged with a time of emission, and so you need to figure out some other way to do that. And so one of the way in cosmology or generally in astronomy is to be able to measure distances. So for the purpose of this talk, if you haven't seen this equation, then let's just assume that if essentially you take the Friedmann equation and you try to estimate what will be the distance of an object, proper distance is essentially an integral of 1 over scale factor from time of emission to now. Okay, so if you can measure distances to these objects, then what you can measure is you can measure integral of A of t, which is not same as A, but at least you have an integral. And so how do you measure distances? There are two ways to measure distances. Most of you probably already heard, but I quickly wanted to go over it. One is a standard candle. So let's say if you have objects where you precisely know what is the luminosity, what is the inherent luminosity, or how much light is emitted by this object, then whenever I'm observing this object, by looking at the flux, which is the amount of light or energy I'm observing, I can estimate distance. So the flux is related to luminosity over 4 pi dl square. And this dl is what we call luminosity distance. Now, this dl is not same as the distance to the object. This dl is related to the distance of the object by 1 plus z. This is what we call basically the metric. And this will be true for any metric theory. So if you have any metric theory of the universe, this scale factor is going to be there. And so the example of a standard candle is supernova, and I've already showed you a result using supernova data, which is a standardizable candle where we already know, based on empirical relations and some of the first principle calculation, that what is the true luminosity of these things. Not exactly, because that's why it's standardizable, and that's how we measure distances. So, but this story is not so much about supernova, although supernova plays a role in when you try to measure this thing. What DESI is trying to do is trying to do something slightly different. DESI is trying to measure baryon-acoustic oscillation, and most of you have already heard about what baryon-acoustic oscillation is. But just for the picture, let me show this animation once. So if you think about a perturbation, initial density perturbation in the universe, where there's a perturbation at some location, there are various components in the universe: dark matter, gas, photon, and neutrinos. So when this perturbation evolves, what you'll notice is that initially the photon and baryons are all coupled. So the red and blue line essentially goes together. Because of the pressure, they start traveling away from the perturbation, whereas dark matter doesn't have as much pressure, and so it's sort of lag behind, and neutrino is just free stream. As this perturbation goes ahead, then at some point what happens is that the proton and electron start to combine, and so photon get decoupled. It's no more coupled to the plasma, and the photons start to free stream. So now you'll start to see that the red line start to separate from the blue line. But the photon already have carried baryons to somewhat larger distances, and so at this point photons sort of free stream and become a background. And you get into this kind of phase. So you get into a phase where dark matter is mostly have this kind of density, whereas baryons have this kind of density. So now at this state, basically gravity is the only thing which is acting, because photon is all gone. And so because of gravity, wherever there's an overdensity, that overdensity is going to try to pull things together and collect and become bigger. And so there are two overdensity here, one is here and one is here. So both of these overdensity is going to try to pull the material around it. So this overdensity of baryon is going to pull the dark matter, and this dark matter overdensity is going to pull the baryon. What is going to happen is that overall, that is going to saturate at some point where they will basically be same, baryon and dark matter. And so as a result, you get to see this small overdensity at some scale. And this is what is called BEO scale. This scale is very well understood in terms of the physics inside of it, right? I'm not making a statement about the measurement, just the physics inside of it. So what I'm saying is that if you look at the perturbations in the universe, there's a scale at which there is slightly more matter. Now this gets imprinted on everything. So when you look at the galaxies, where are the galaxies are going to form, there's going to be slightly more galaxy at this particular scale than any other scale. So if you look at all the things. And now this is happening everywhere. This is not just one perturbation, it's happening everywhere. So imagine a superposition of all such perturbations everywhere in the universe, and that's what you'll see at the end. So this is what the BEO scale is. And then this is quantified by this quantity RD, which is essentially estimate of how far this baryon photon plasma is going to travel before decoupling. And that's given by this equation. So this RD is a scale which we understand very well. Now, we have also measured it very well from cosmic macro background, but let's say just the fact that we have a scale which we understand very well and we know it's going to be same at every epoch in the universe, now you can claim that it's a standard ruler. So if there's a standard ruler of size L, then you already know L. You don't know the value of L, you just know that it's something constant. Then you can estimate that, use that to measure the scale of the BEO, and that scale of the BEO is going to give you distance, right? So again, if you know the size, you know the angle, you can estimate the distance using this geometric relation. And this distance is called angular diameter distance. Again, since we are in a metric theory, this will be same as proper distance to the object. And this angular diameter distance will have an additional factor of 1 plus z to connect it to the proper distance. And to remind you why we are trying to look after proper distance, because proper distance is an integral of a scale factor, which is what we want to understand. And so this is what is called baryon acoustic oscillation. If let's say I want to measure the same thing along the line of sight, again it's the same scale, which will be, same feature is going to be visible along the line of sight. But since the line of sight, there is also a Hubble flow which is involved in this thing, you are going to be sensitive to slightly different characteristic. You are going to essentially be sensitive to what is h of z, what is the Hubble rate at that redshift. And so by measuring the line of sight BO, you are going to measure this quantity dh. By measuring the perpendicular to the line of sight BO, you are going to measure this quantity dm. And if you don't know the true BO scale, then all you can measure is dm over rd and rd over dh. Basically, you're measuring the ratio of this whatever true BO scale is to whatever you are going to measure. So, yeah.
I didn't understand what is delta z line of sight. I could understand angular one.
Right. So this the BO feature is not aligned to your perpendicular to the line of sight. It's there in all different directions because the way I explained it. So when you are going to try to measure it, you can measure this scale both perpendicular and parallel to the line of sight. Right? The perpendicular to the line of sight will directly give you distance with metric term. The parallel to the line of sight will again, since it's not associated with delta theta, it's not going to give you a distance, but since you already know that the scale, it is by measuring this scale, you can estimate what is the expansion rate of the universe at that scale.
So
again,
to measure something parallel to the line of sight, you need to have galaxies that are, you're looking at things which are not exactly coincident, but roughly coincident.
Yes, yeah.
And then you
right. So you need galaxies which are roughly coincidence for that. So that's the line of sight mode. You don't necessarily have to really sort of separate these things out. I'm separating it just for the purpose of explaining there are two terms involved. But what you measure is that you measure this scale at all different angles. You measure as a function of angle from the line of sight. So yeah, so that gives you this BO scale. But since I haven't told you how to measure RD, so in absence of really knowing the size of the scale, all you have access to is the ratio of these scales rather than the absolute value of this scale. You can also combine and look at the isotropic form of this scale, and that's what we call dV. So it's nothing but it's a linear combination of these two scales. The dm square is because they are two different directions, right? So you can measure dm over rd, rd over dh, or you can measure dv. Right. So this is now an example of showing a BEO result from one of the previous survey. So this is one of the galaxy survey called EBOS, where we have measured this scale at 100 megaparsec over H in a real survey where the red points are measurement and the error bar. So let me just quickly tell you how do we measure this scale. So what we are really talking about, since these are perturbation and these perturbations are sort of superposition at every location in the space, you can try to measure 2-point correlation function, because when you try to measure 2-point correlation function at each point, you expect to have that perturbation, and you expect to have overall over density. So that's what we are trying to measure. We sit on each galaxy in our survey. Let's say we have a survey where you know 3-dimensional position of many galaxies. You sit on each galaxy and count how many galaxies you have around it as a function of distance. So this is what this circle means. And then you go and sit on the next galaxy and you do this and average over all of that. So this is what 2-point function means. When you plot 2-point function scale by s square, the reason you have to scale by s square simply because you want to see it by eye. Otherwise, the scale is going to exist anyway. But to highlight that, and that's what gives you this measurement of BEO scale. So to measure this, you need to measure 2-point function. To measure 2-point function, you basically need 3-dimensional positions of many galaxies. The way we measure 3-dimensional position is, first of all, we measure position on the sky, RA index, and then we try to measure redshift, which is what connected to the scale factor that requires a spectroscopy. And so DESI is all about this redshift. DESI is all about efficiently measuring large number of redshifts so that we can measure this 2-point function very precisely and hence get to BEO scale. You can also think about this picture in Fourier space, and it's helpful in terms of illustrating some of the points which will come later. So rather than looking at configuration space where trying to count number of galaxies as a function of distance in scale, what you could do is you could take your galaxy survey, you can make a grid, and you can do a Fourier transform of your density. Now, when you do Fourier transform of density and correlate those Fourier transform of the density, this is what is called Fourier conjugate of correlation function and its power spectrum. Now, a peak in configuration space is going to appear like a wiggle in Fourier space, and so that's what you see. It's again using the same data measurement of the power spectrum, and you can see this very faint wiggle on that, and that can be measured with roughly 2% precision in this data set. Now, what you'll also notice is that if you look at this galaxy power spectrum, which is what is measured, compare that to what you expect the power spectrum of the overall field, the entire matter distribution in the universe, then there is a difference in the amplitude. So this is the matter power spectrum, assuming lambda CDM model, and this is the galaxy power spectrum. This difference is caused by what we call galaxy bias. So for the purpose of this talk, you can say, okay, all the messy astrophysics and things like that is causing what is the exact amplitude of this. But essentially what is happening is that if you imagine that universe is a Gaussian random field, which is actually very close to true as far as our observations are concerned, especially in the early universe, then if you look at the peaks of the Gaussian random field, so let's say you draw a threshold and you can only see the peaks, then what you'll find is that based on BBK's model is that the power spectrum of the peak is same as the power spectrum of the total matter field multiplied by a constant amplitude. So this is what is called galaxy bias, and that's why the amplitudes are different. So that is something we marginalize over in our modeling. Okay, so now that I've told you that there's this big physics implication for if you can measure dark energy equation of state, but if you want to measure dark energy equation of state, what you're really trying to sort of physically interpretable thing is you're trying to figure out how the universe is expanding as a function of time. What is really the details of the expansion? I told you that you can measure details of the expansion if you can measure redshift and you can measure distances. So if you can measure distances and redshift both independently, that is sensitive to, that's actually integral of 1 over A, and so that is going to allow you to measure things like dark energy equation of state. And this can be measured, yes?
So when you actually translate these to W, you assume something about the dark matter, that it's just falling off as 1 over A cube?
Yes.
I suppose the dark matter was decaying into radiation, invisible radiation. Will that spoil this event?
So we have assumed that for dark matter, this is W equals to 0. The equation of state is equals to 0. If you change dark matter W equals to non-zero, we haven't done that exercise. But my feeling will be that it will not, because dark matter-dominant area is actually at higher redshift, and we have very precise data to constrain that. Also, there are lots of early universe CMB constraints on this decaying dark matter model. There are like hundreds of papers about that, and all of them haven't detected any deviation, and the constraints are getting stronger and stronger. But for this analysis, we assume that dark matter is just stable and conserved. We didn't assume any decaying. Right. So you can measure. You can learn about these kind of physics by essentially tracing this. You can do supernova measurement and BO measurement. For BO measurement, I've told you that you need to have large number of galaxies localized in 3-dimensional space. But this has been done, right? So this has been done over last 20 years, and Shubha has talked about this in the morning, and he showed BO results from SDSS and BOSS and EBOSS. And so the question is, and SDSS and BOSS and EBOSS have done 2% measurement of BO. So that's already remarkable and very hard to do that kind of measurement already. If you want to improve a precision about that, it's very important to understand how to improve that and what really matters. And so this is one thing I want you to take away from this talk is really what aspect of the thing matters. And so simply speaking, what you'd want to say is that, okay, let's measure more and more galaxy redshift, and hopefully that will give us more precise measurement. But that's not quite what will work, in fact. You'll have to look into a little bit more detail. So to measure spectra, you first have to identify the location of these galaxies in the sky. And so you have to do what we call photometric survey or imaging survey, essentially mapping the sky night over night and taking very deep images. So this is an image from DESI legacy imaging survey, which ran over 6 years, which we did precisely to select targets for DESI. Now, a survey like this, you can see lots of galaxies. Each little blob is a galaxy here. You can hardly see them with the resolution of the projector, and probably resolution of my image. And there are some artifacts, and there's this big galaxy. So if you just do a statistics in this imaging survey, what you'll find is that we have detected about 1.5 billion galaxies and 1.3 billion stars. So those are the numbers which you'll be able to see given the imaging limit. And future survey like LSST and Euclid is going to make this look like a very tiny thing. So the numbers. This covers about 20,000 square degree of the sky, 18 to 20,000 square degree of sky. We always sort of do not observe if you're interested in extragalactic sources around the Milky Way plane. And so that already reduces some part of the sky. And so this is about 20,000 square degree. Okay. Now, so if you want to measure 1.5 billion galaxy spectra, of course, you don't want to do it one spectra at a time. You want to do some sort of parallelization. And so what DESI said, okay, let's try to do make an instrument where you can measure 5,000 spectra at a time. So you can measure 5,000 galaxy. If that is your capacity, but at the end of the day, what happened is that you get about 4,000 spectra at a time because of various reasons. Let me not get into that. You observe about 8 hours a night. You observe for roughly 30 minutes per spectra. Just roughly the number which in the ballpark of DESI, you get 64,000 spectra per night. How many years do you have to observe this for 1.5 billion galaxy? I'll not tell you, but you can calculate that. But let's say if I observe this for 5 years, if I do a survey for 5 years with a 0.5% efficiency, because night sky is not always favorable, you get about 58 million objects. DESI is planned to observe about 40 million objects. So that's the ballpark number you are going to look at. This number is not really anywhere close to 1.5 billion galaxy. So what do you do? The problem is that you can measure, even with an instrument like DESI, only 4% of the objects you see in an imaging survey like DESI legacy imaging survey, and this ratio is going to become worse and worse with the future survey. So how do you select? So you have to select, you have to choose, and you have to be very picky. You have to choose this 4% object from the thing so that you can get best cosmological constraint. And answer is definitely not select the brightest object, right, which is easiest to measure. If you select the brightest object, it will be easiest to measure, but that will not get you a good cosmological constraint. So let's think about signal to noise, like how does the noise really gets estimated and propagated in this kind of measurement. If you think about measuring power spectrum or correlation function, typically the power spectrum amplitude itself is roughly in this region, 10 to the 3 to 10 to the 4, and that is something not really in our control. That's really how the universe is. We can't change that. We can't increase that by a large amount. We can observe cluster, but then there will be very few of them. So this is sort of given. So you can try to reduce the noise of your measurements. So you can try to reduce the noise of the power spectrum. And the noise of the power spectrum, and again, this equation I'm not going to explain, but what it is that if the universe is a Gaussian random field, and if you're trying to measure this through point traces, you can essentially do a mode counting exercise. You can do calculate what is the number of mode you have in the Fourier space as a function of volume, and that's what gives you this relation. And so this is what the estimated noise looks like. What you'll notice is the volume of the survey is there. So if you have higher volume, you'll have lower noise. So one key thing is to measure larger volume. So it's not number of objects. And then other thing is this is a number density, and so this is what we call short noise, 1 over n bar, which is added to power spectrum. Power spectrum is sort of fixed. So maybe you want to think about, okay, how do you sort of reduce the effect of short noise? As soon as you make this term subdominant compared to that term, you're not going to be short noise dominated anymore. And so this essentially tells you, okay, you want to measure large volume, and you want to roughly be in a regime where 1 over n bar is less than 1 over p, and that essentially gives you that you want to have a number density of galaxies roughly of this scale. So number density and volume is important, not the number of objects. So just pure number of objects is not going to give you the best constraint. You don't want to go to very high number density, but you want to go to very high volume. Now this is a difficult problem. So first of all, physically now you know what kind of thing you want to optimize. You want to optimize number density. You want to be roughly 10 to the minus 3 objects per unit volume, and you want to maximize volume. So this is a hard problem, and this gets you a lot into the astrophysics of galaxy. You need to understand and being able to observe a spectra. I'll not tell you all of the details, but let me try to illustrate the main point. So if you look at the percentage error on BEO as a function of redshift, what the white line is telling that if you are going to measure something like 14,000 square degree, which is what DESI is trying to do, this is the cosmic variance limit, which means you cannot do better than that in 14,000 square degree, simply because it's limited by the volume you have at each redshift. Now, what the DESI error bar is going to look like is this red line. So at low redshift, we are very quickly limited by cosmic variance, and hopefully, Rajesh, this sort of tries to answer your question why our errors are larger here. So even, in fact, we actually have our number density of galaxies much higher than you need here, but we are limited by this cosmic variance at low redshift. And then at higher redshift, we are limited by what kind of galaxy we can select and how efficiently we can measure. And so what happens here is that at sort of middle redshift, around redshift 0.5, you can very efficiently measure really the bright galaxy. So these are living in massive halos up 10 to the 13, and so we just measure that, and they are quick to measure. They are very nicely, redshifts are very easy to measure. This is one of the most easy thing to do. This is what SDSS had already done. Once you go to slightly about redshift 1, you can't measure this kind of galaxy with this kind of instrument. You need to have a much bigger telescope. You need to integrate for much longer. So that's not going to work. And so what happens is that there are these interesting kind of galaxies which are called star-forming galaxies. The full spectra may be faint, but they have this special feature, which is O2 line, which is what I also showed in one of my illustrations. So they have these lines which are very bright. So these lines are much brighter than the two overall spectra. So if I want to detect the overall spectra, I'll have to integrate much longer, but I can detect those lines very quickly. And hence I can measure redshift very quickly, which is what I am after. So that's why the targeting around redshift 1 is looking at this kind of galaxy, star-forming galaxy. And then you have to think about how do you sort of select it without looking at the spectrum. Now at redshift 1.6, what happens is that this O2 line drops out of our spectrum. So it gets redshifted and we cannot see it in our spectrum anymore, which is why we don't have this galaxy beyond this redshift, so at 1.6. Now what do you do if you want to go to higher redshift? Then the only thing you can measure is the very bright quasars. So these are objects with supermassive black holes who are very bright, they have lots of features, and so even at very high redshift, we can measure that with this small instrument. And so we measure these quasars, and then if you go to redshift beyond 2.1, which is not plotted here, then what you can also see is that in front of this quasar, there's going to be Lyman alpha forest, which you can see and then measure BU scale in that.
But what if there is some dynamical effect which makes slight difference in the BU scale for these different kinds of objects?
Right. So that's a very good question, and Nikhil sort of tried to show that is this is part of our theoretical systematic budget, and we have to do a lot of simulation and careful analysis to test for those effects. These are normally come under what we call assembly bias effect. So basically, the fact that we are looking at different kind of galaxy might have different relation to the dark matter. Maybe you're looking at a specialized region of the cosmic web and not sampling the density uniformly or whatever. And so those are the possibilities. If you look at the hydrodynamical simulation, you do expect to see some of those effects. So far in observation, and especially for DESI, we haven't detected this at the significant level. So all those effects, as far as our analysis is concerned, will cause a fluctuation of 1/3 of our statistical error bar, smaller than that. But that's actually a very key issue we are facing. And as the precision is going to get better, we have to do this hard job of trying to estimate that there is no additional effect which is causing any kind of bias. So to make sure that you're actually sensitive to cosmology rather than galaxy astrophysics. Right, and so yeah, you can hardly see this, but what this is an illustration of essentially in terms of the spectra, how these different kind of objects looks like if you were to plot the spectra, and then it's plotted with look back time, and for different models are also plotted here. So I hope now you have some idea of how to go and design this kind of survey. Maybe not all the details, but at least what are the main thing you want to think about. So very quickly, now that you already know how to design the survey, let's just very quickly look at the instrument. This is DESI Mayal telescope, and DESI instrument is basically this thing. It's very heavy on top of the telescope, which moves around with the telescope. So you're always scared that someday it's going to fall. Just kidding. So DESI is a 5-year survey, 2021 to 2026. We already have 3 years of data. It's going to observe 40 million spectra. In terms of the instrument, one of the major breakthroughs is that previous survey had to be plugged in. The fiber had to be drilled hole on the aluminum plate and then plugged in for each field, each part of the sky you're going to look at. Now we have this robotic fiber plane which can reconfigure itself in less than 1 minute. So you go to the part of the sky, you ask this optical fiber to reconfigure, I want to observe these galaxies, they are going to reach in less than 1 minute. So that's how you get the efficiency and increase number of objects. So this is another view of the DESI focal plane which I showed you. There are 5,000 holes where there are 5,000 fiber positioner which can observe 5,000 spectra at a time. And if you blow in one small part of the hole, these are the regions in which each of these fiber can observe. And one of the difficulty you're going to face when you're going to do that, this is actually taken as most of amount of time in terms of the analysis, is that each of these circles have one fiber. So you can measure one spectra in each of these circles at a time. And what you can also see in the background with these different color circles, I'm not sure how much of that you can see, is these are the targets which we want to observe. And so what happens is that sometimes, for example, in this region, there's one object which you want to observe, but there's no positioner. So we cannot observe this object unless we come visit again this part of the sky with slight dither and then have one of the fiber reach there. There's a region where there are almost 9 objects within one fiber positioner, but we can measure only one of the spectra. And so what's going to happen is that the instrument is going to cut your density field by some factor, and this will be function of the density field itself. So imagine you're trying to measure power spectrum or density field, and now your instrument sort of put different threshold in density field at different locations, and you're going to measure the power spectrum of that thresholded density field. You're going to get very different thing. You're basically destroying your 2-point functions of the data. And so to address that, a lot of things needs to be done in terms of how many times you want to visit certain part of the sky, being efficient, and how to deconvolve this aspect of the instrument. So this is what we generally comes under the fiber collision issues in terms of the clustering. And this is going to be, this is actually, for at least for BOA scale, this is not such a big problem because it's large enough scale. But for further analysis of this two-point function, it's going to be a big headache, and we are trying to handle that. So let me just give you a quick summary of what all things I've told you. You can start by looking at an imaging survey. So you first start and do a survey for 6+ years with 3 different telescopes, 18,000 square degree, 1.5 billion galaxy. You build a DESI instrument with 5,000 optical fiber or positioner, which takes 10+ years, costs 600 crore rupees, and it also costs 600 crore rupees to run it for 5 years with 700+ team members. You think about, okay, how do I figure out what galaxies I can observe, because I can observe tiny fraction of galaxy which is there in the sky. So you try to write down based on really the first principle. You try to approach this NP equals to 1 and make sure that you can observe the spectra of right quality in 30 minutes. And so that gives you essentially 6 million extragalactic spectra. This is what is there in DESI year 1 data. You spend a lot more time to estimate errors on these measurements, and then you spend a lot more time tracking non-idealities, like I just showed you about the fact that your instrument is going to threshold your density functions. So when you do all of that, you get measurements of two-point correlation functions. This is what Nikhil already showed in the morning. These are different kind of samples I already told you, just trying to be NP equals to 1, number density of 10 to the minus 3, 10 to the minus 4, as large volume as possible, given the amount of time. And you can measure BO scale in each of these redshift. As a function of redshift, you can really figure out where is the location of the peak, and that's what you're after. All you're using here, there's a lot of information actually in this plot. These are correlation function, the amplitude of the peak is also sensitive to cosmology as well as galaxy astrophysics. All we are using is trying to figure out where is the location of the peak. So that's the BO scale. That is much more robust. That's why we are looking at that. And so if you plot the BO scale, as I said, you can measure isotropic version of this, which is dV over RD, and you take a ratio of that with Planck lambda CDM prediction. So you take CMB as the best guess, and you take the ratio. These are the values of this BO scale as a function of redshift. So these are the measurement and the error bar coming from these different traces. If you plot on top of that a W0 WA CDM model, which is DESI best fit, that goes roughly like this. Right? So this is the distance measurement I've been talking about with redshift and distance. These are the integrals of 1 over A, which you can then go back and now try to model at the level of cosmology.
In these graphs, you need the Hubble constant or insensitive?
So in these graphs, these are all in co-moving units. We always work in co-moving units, so you don't need Hubble constant to plot this. So Hubble constant is essentially factored out by dividing by h in your distances.
So DESI data cannot detect Hubble constant.
It can. So that's what the line of sight BAO is sensitive to Hubble constant, but not entirely Hubble constant. So if you just look at the DESI data and try to see different samples and different redshift, are they consistent with each other and what are the different constraining power? So what you can detect is H0 times RD. So you can detect Hubble constant times the size of the BAO alone. Now BAO you can have from BBN or CMB and things like that, but DESI data itself do not have access to Saunders resonance scale, or like what is really the your standard ruler. So you can measure H0 times RD, you can convert this into omega matter, and what you find is that these different samples are all consistent with each other, but they have different degeneracy. As you go to larger redshift, you are able to constrain omega matter better. As you go to lower redshift, you are more sensitive to Hubble constant compared to omega matter. Right, this one, right? So all the measurements, since we are not doing these measurements per galaxy, what we have to do is we have to combine a lot of galaxy to measure the correlation function and then measure the BA scale. So we don't have measurement of BA scale per galaxy, and hence we have to bin all the galaxies in redshift bins. And so these are the redshift bin, and these are plotted at what we call effective redshift. So effective redshift is calculated as the ratio of the pair of the redshift summed over all the galaxies. So that's because we are looking at two-point function, it's the pair which is important. And so these are all plotted at effective redshift.
So here, if you put the RD from CMB, what do you get for H0?
If you put RD from CMB, then you get H0 equals to 68 point something, which is 1 sigma or roughly 1 sigma above Planck value and about 3 sigma below supernova, if that's what you're asking about. So you get very consistent with CMB if you put RD here. Right, and so now you can ask, come back to this question of dark energy equation of state. How does the dark energy equation of state looks like? In place of plotting as a W of Z, and now I'm showing in terms of the real parameters. And so what you see is that just the DESI BU itself is consistent with lambda CDM. These are 1 sigma and 2 sigma contour. If you combine it with CMB, then you start to see this 2.6 sigma deviation. And then if you combine it with supernova data, that reduces the error bar because it's sensitive to the same kind of physics. You get various different level of significance of this thing. Omega M?
Omega
WA equals to, W naught equals to
minus 1 is ruled out?
Since this is a 2-parameter thing, you need to talk about ruling out in 2-dimension space, right? So W naught of -1 and WA equals to 0. If you compare with that point, then these are the significance in terms of how significantly you rule out, right? So that statement has to come with a number, like what is the confidence at which you rule out. So with DESI plus CMB, it's 2.6 sigma. If you combine with supernova data, then depending on what you use, you can get up to 3.9 sigma. You get about the same ballpark, around 3 sigma. We have done that exercise.
And is this something related to Hubble tension also?
No. So when we look at there's an issue called Hubble tension, which is basically saying that if you measure Hubble rate with supernova data, and if you measure Hubble rate with CMB data, they are different. Supernova gives you roughly 73. CMB gives you 67.5. And so they have 4 to 5 sigma tension. So that's what Avinash is asking about. Here, Hubble tension is not a problem because the way we use supernova data is that we don't use the full supernova data. We only use the magnitude of the supernova itself and how they are evolving. We don't use the lower part of the descent ladder. In another word, we essentially allow MB to be free. And so the Hubble constant cannot be measured with the part of the supernova data we are using. And so there is no tension in that case.
Let's say if we use this omega naught and omega A, whatever the best fit, omega naught and omega A, and include it to measure the H naught from both CMB and DESI BOA and these things, can we kind of the Hubble constant that we measure, is it kind of getting nearer than the Hubble tension?
So if you combine with DESI data and measure the Hubble constant, this is what Ashoka just asked about, you get a Hubble constant of 68.5, which is closer to CMB than supernova. Now within lambda CDM you can combine it, but there is a tension, so you do not want to combine it. We haven't done that exercise. You'll get some answer, but we haven't done that. Yes.
If you take the Hubble constant from supernova, then you can combine your data to get RT.
Yes.
That is in conflict with something that you know definitely.
No. So if you plot our measurement of Hubble constant versus RD, it will be a band, and now you can combine it with CMB in terms of the RD, or you can combine with supernova in terms of H naught. That will give you a different RD. That RD will be inconsistent with CMB.
But so you can say your result may also be consistent in supernova, but then CMB is wrong.
Yes, in that case, but then BBN also have, so if you just take that value, if you take the Hubble constant in terms of the supernova, then that will be the case. Our RD, the resultant RD will be different from the CMB, but then there are CMB measurement from the BBN as well. which will again also be inconsistent.
Yes. I mean, your first two, the values of W0, WA seem to be roughly the same, but the third one is quite away from the other two. Is that, I mean, the last set of...
Right. So given the error bar, these are all sort of within 1 sigma of each other, right? You can see just by these are overplot. The issue here is that
the other one seems to be, I mean, the plus minus 0.067, whereas that's 0.1 away. I mean, right? I mean,
you mean
the W0.
Yeah. So in terms of just the W0, if you look at these error bars,
they're kind of at the edge of.
This is about 0.1, so this is little more than 1 sigma. So that's basically, if you look at this magenta contour and then compare that to green contour, right? So the best fit value is not going to be within the shaded region of each other. That's the statement you're making. The difficulty here, so in terms of the DESI analysis, we have basically said that you have to take this with a lot of care and you have to dissect this very well. Because just supernova themselves, there is a lot of common supernova between these different samples. These are not entirely independent samples, so you cannot combine them together. And then there are some inconsistency between supernova itself if you look at omega matter and things like that. So this combination is something we need to dissect more, which is what many people are sort of looking at more carefully. Our headline result is more here, which is 2.6 sigma without supernova.
Yeah, because these figures from combining seem to be very different.
Yes.
What you get, I mean, the W0 there versus the W0.
Right. Yeah, and the errors are sort of big enough to have that fluctuation. And so, okay, so this is the current result. Yes. Yes, W0 and W are two independent parameters. So that will depend on the macroscopic picture. There are people who have done analysis where there's for example, a model called Mirage model, which will give you a relation between W0 and WA. We can do that analysis and then you'll again get a constraint, but then you'll be doing under that particular model. What we are saying is that we are more free. And then if you assume a model, you get even a stronger constraint power, right? Because you're assuming a relation between them. In this analysis, it's all, both are independent. Right. So, okay, what would it look like in terms of the future? I've showed you results from the year 1 of DESI data, but let's say if we have the 5 year of DESI data, we can already do forecast. We don't have the result. If you were to do the 5 year of DESI data, and if you combine that with supernova and CMB, this is the pink contours is what you expect to measure. So if this holds true and stay at the same central value, just the error reduces, then this will be a 5 sigma deviation. But we'll have to wait and see what it's going to look like. But the fact that the error is going to reduce significantly enough in next 2 years, with just next 2 more years of data is very exciting. And so we are really trying to ramp up our analysis with the year 3 data and then year 5 data. So Ajit, I think it's already 1 hour. How much time I have? 5 minutes. 5 minutes, yeah, good. 5 minutes is really good.
So this reduction of error that comes over here is just adding more DAO data, but you will have RSD also.
Yes.
Does the RSD with the first year data, does it make a difference?
So far, we haven't looked at the forecast for that, but in principle, RSD should help. We are doing the RSD analysis currently. It's all blinded. We haven't seen the result, but it's hard to say. It depends on certain aspect of the analysis itself, in the sense that what parameterization you use in detail. Just to give a broader picture here, what Shubha is asking about is redshift space distortion. So in these galaxies you're observing, these galaxies are dynamically interacting with their environment, right? And so they are not just sitting there ideally. So because of that, they will have peculiar flow. So they'll be moving around. This peculiar flow is going to add an additional Doppler term. The line of sight component of the velocity is going to add an additional Doppler term. This Doppler term is part of our redshift measurement. And so that will allow us to measure what is the average velocity of these galaxies. This is what, in a sense, redshift distortion measurement is going to give you, and that will give you majorly constraint on growth rate. So sigma 8 is what within lambda CDM, sigma 8 is what you can measure using that, and so will that help with dark energy equation of state? So not directly, but indirectly by breaking degeneracy, it can help. But I don't know the final answer, how it will look like. Mm-hmm. If you look at the macroscopic model, there are models with lots of oscillations. So in principle, you can model even with a sine function or a higher order polynomial. So in terms of macroscopic picture, yes, it's a lot from the model point of view. But from the data point of view, since so far we haven't been even able to detect WA different from 0, we are still 2-parameter model. We are still not in the regime to introduce more parameter. There are papers, you can find this, I think the first author is Kush Lodha, who have done a parameter independent reconstruction, which means you don't assume a parametric form. But let's say if I try to do through a Gaussian process where W of Z can be free at many different epochs, how will it look like? And they've done that. They have to assume some priors there, and that looks very similar to our bottom line result. Right. So beyond dark energy, in the interest of time, I'm going to skip over neutrino mass, but that's also an interesting constraint. What I want to talk about is actually even redshift distortion. I've already told you. So what I wanted you to take from this talk is that I've talked a lot about cosmology, but there are many different facets of DESI where you can look at many different things. And so one such example is that, like, this is a map, a small part, and this is not from DESI, this is from eBOS, where we have a map of these different kind of galaxies. These quench galaxies, these are quasars with supermassive black hole, these are star-forming galaxies which are colored in different ways. And so what you have access to is that you have access to the information about where these supermassive black holes are bright. And so you can think about various different physics operating, how do these supermassive black holes grow, or why do they become active. If you write down any of the model, most likely a lot of these models is going to predict certain specific feature in terms of how these galaxies are going to correlate, depending on what kind of model you're going to like. For example, one thing I'm right now toying the idea of kick velocity, which I was talking to Nishi a little bit about. If let's say if your model is that galaxy central supermassive black hole become active whenever there is a merger, and then merger will cause also a kick velocity, can you sort of measure this kick velocity with a survey like DESI? And potentially, if you just think about the physics, you should be able to in certain regime, but whether you can or not is a different question. So what I want you to take is that apart from the headline cosmology, there's a lot of rich data set, and you can ask these detailed questions. The data is rich enough to ask these detailed questions and address that at various levels. There are large number of things, but these are just the things of my interest. But there are many more things. You can look at relativistic effects. So how do the light from this gravitational potential of the dark matter around which galaxy is living climb up, then what is the effect of that? That's the gravitational redshift. Can you measure gravitational redshift with a sample like that? And based on our estimate, we think we can measure gravitational redshift in the next couple of years. You can look at the boundary of dark matter halo. Dark matter halo are these collapsed objects, but is there a boundary? How do you define the boundary? So this is particularly called splashback radius. You can construct models of dark matter by looking at tidal stream in the Milky Way, and we have precise measurement of spectroscopic measurement of tidal stream in Milky Way. So you can look at various different possibilities there. You can look at life cycles of galaxy. You can also look at, in terms of the fundamental physics, you can look at beyond Gaussian term in the initial condition. If the initial universe was Gaussian or were they non-Gaussian term, that is going to affect very large scale clustering. That's going to affect large scale 2-point function. And that's another analysis which is going on right now within DESI. So yeah, with that I will end, and basically I hope you have some feeling of why we are looking at all this complicated different kind of galaxies, and how do you sort of go about designing this survey, and what are the challenges about it, as well as some feeling about what does it mean to measure dark energy equation of state, which is evolving, and what are the physical implication of that. With that, I will end by saying, okay, please go explore. It's a rich data set.
Thank you, Shadab, for this very nice overview and very clear summary of the current results. We had many questions, but are there more?
We even need a second coincidence. Sorry, I just wanted to ask you.
May even need, so this is about if dark energy equation of state crosses -1. Now in that case, you need more than one field. So one field itself is a coincidence, the lambda being 0 is a coincidence. Now you need two fields. Now two fields needs to be tuned to have this behavior. One of them have to be phantom, as Ashok said. So you need to explain what is the second, why there is a second coincidence. And very early on I showed you.
Sorry, what is phantom?
Negative kinetic. Oh, negative kinetic.
Good thing.
So this acceleration is acceleration, then deceleration, and going to 0. So this has to, this needed the second coincidence to go back in the future, which we cannot see, unfortunately.
Okay, yeah, this is about the connection to the last talk. I mean, did I understand correctly that this eROSITA, they found perfect agreement with lambda CDM? Is there a direct conflict with this result, or?
No, so they do not have access to the aspect of dark energy at the similar precision. So what they have found is they have found consistent with lambda CDM in terms of the omega matter sigmoid plane. If you look at our omega matter sigmoid plots, then we will also have consistent result, and our result is much more precise. So in terms of dark energy equation of state, they have only looked at constant dark energy, which is non-evolving, and that is consistent with -1, which is the case for even with our result because it evolves across redshift. Yeah, I don't think I have a plot for omega matter sigmoid, sorry, but our plot is also consistent with lambda CDM.
So that means if you assume that the dark energy is not evolving, then W equal -1 is the best.
Yes, but it might be because dark energy is evolving in such a way that the average is equals to -1 is best. So even with DESI data, if you just do one parameter deviation, you find that it's consistent with -1.
You mentioned the boundaries of the dark matter halo. Is that the same thing as the boundaries of the voids in the web?
No, so these are very different things, right? So void is not something which is gravitationally collapsed and held together, whereas dark matter is a gravitationally collapsed object. Boundary of void is a bit more ill-defined. We don't have a very good definition of boundary of void so far. But boundary of dark matter halo is really thinking about, if you think about objects falling into dark matter halo, there's going to be one orbit which is going to be just fall in, and there's going to be one orbit which is just going to just not fall in. And so that is the region which is what we call splashback radius, which you can detect and measure in the real data.
And that continues to be well defined as the universe evolves.
Yes, because it's so since we are talking about like really very physics-based concept here, which is an orbit. Given let's say a dark matter potential, you can always define that orbit where things are just going to fall in versus just not falling in, and that's a very well-defined quantity. So that should continue to be well-defined. But in terms of the measurement, we are in the early days. We have very few measurement for the cluster, so it's really very massive halos where you can see this. You cannot see this for typical halos.
Sorry, I was a bit confused. You said if you just use the one parameter thing in the equation of state with the W naught, that's consistent with it being, with lambda being -1?
Yes.
So how are, I'm sorry, a bit confused. How are both of these statements okay? That one parameter is okay with it being -1, but if you use a two parameter.
One extreme example is that imagine dark energy equation of state is oscillating sinusoidally around -1.
Tracing the averages.
And so you can still be average to -1. And same thing is true for our evolving. If you look at the average, it will be close to -1.
I see. So, but now if you focused on some region of redshift, and can you then improve your sigma and see if it deviates away from -1 more, with higher significance if you focused on a particular redshift and said, this here it's significantly away from -1.
So this is a statement about like how precisely you can get these measurements, right? And that's limited by cosmic variance at any redshift. So we are limited by this red line. If we fix the area, white line, we cannot be more precise than that. Now you have to see if this error is small enough to, if you take the best fit model at one of the redshift, you can do that quantity. But even then, what the problem is going to be is that a lot of these things are coupled. If I can change omega matter, that's going to affect my overall expansion rate. So I am not measuring just the dark energy state. We are measuring all cosmological parameters together. And so you need to break that degeneracy, which is why you need all the redshift together. It will be hard to do that with just one redshift. But what you can do is, let's say you assume all the cosmological parameter based on some other measurement, and then now see what will be the measurement for BA scale at some redshift given this definition. You can do that, you're limited by cosmic variance. So you have to see if your deviation is detectable at this limit, or you need to increase area.
I see. So at lower Z, you are doing as best as you can, but at higher Z, you presumably can do a little bit better.
So at higher Z, we can do slightly better.
But have you done a Bayesian odds ratio between the lambda CDM model and the two-parameter model?
Yeah, so we have done an evidence calculation, and the evidence calculation gives you the same as our 2.6 sigma result, which is also, so you can do chi-square difference, you can do evidence calculation, you can do the likelihood difference. All of that for DESI plus CMB gives you roughly 2.5 sigma.
So the two-parameter model is preferred over lambda CDM by 2.5
sigma in all different methodology. And so the precise numbers are there in the paper for evidence and likelihood ratio. Ashok?
No, a very naive question, which is why did DESI choose the optical frequency? Wouldn't you maybe have seen more in radio or other things?
Radio is much harder to do, right, in terms of the spectroscopy and precision. So first of all, the first issue with radio is that the resolution is very limited in terms of the single telescope. So if you want, because of the wavelength, it's limited by the size of the wave, and lambda over d limits your resolution. So you cannot resolve many of these things as easily as with a single telescope. So if you want to go beyond single telescope, then you have to do interferometry. Like GMRT is an interferometer. Now you have to take several telescopes and interfere the signal, which is then much harder and much more complicated system than doing a simple optical thing.
And even shorter wavelengths, I guess it's less.
And then the last part is about the signal. So radio is very sensitive at 20, like for example, 21 centimeter signal. So in fact, there is radio survey to do BEO, which is SKA. But that's not going to do as good as DESI in these redshift, but it's going to do better at higher redshift.
Yeah, is it possible to fit the data with under the constraint that W is always larger than -1?
Yes, it's possible to do that.
And
I think if you'll do that, you'll get basically -1.
W equal to -1.
Because it's all -1 itself, we have a small error bar of 0.1 around -1, right? Now imagine in that likelihood you put a floor.
Yeah.
Right, so imagine a Gaussian, which is go around -1 with a 0.1 as the width. Now you put a floor, you're basically going to one-tail distribution with the best fit at -1.
I see.
It's similar to neutrino mass, where the neutrino mass, you get 0.
I see, okay. Yeah, because W less than -1 is very unusual, right? Meaning, okay.
Yeah, it's unusual, it's not something we were expecting, but...
yeah, meaning it's very hard to find a unitary theory with W less than -1.
Since it is both, the -1 seems to come from the small redshift part, and less than -1. Is there some systematic? Oh, I think
Less than -1, 1 minus A.
Yeah, less than -1 comes from the large redshift. Yeah, less than -1 comes from the large redshift. This comes into the more stable region at low redshift.
I want to follow up on this. I think one of the speakers in the morning very strongly argued that there is practically no systematic errors that would affect these conclusions. But Is that
no, so like in this kind of statement, right, whenever you are doing them as measurement, that statement always is going to be made, right? There's no systematic error which affect my measurement. Why? The reason is that you have to do all the robustness tests. So anything we can think of, we have done robustness test of that. And that robustness test will give you a systematic error budget, which is part of our error budget. So let's say even if you have 1 sigma systematic, then eventually what we are going to say is that our errors are twice the actual error, and then we'll say we are not affected by systematic. But then the systematic error budget is going to be significant, and so you have to be concerned about that. Right now for DESI, based on all possibility, including astrophysics to nonlinearity to reconstruction, to issues like imaging systematic, which I haven't talked about. We have looked at how much BO scale can shift in our measurement based on our analysis methodology, and this is all within 1/3 of the statistical error bar for year 1, which is not same for year 5. We'll have to repeat this exercise, and that gives you an error budget of 5%. So our final quoted error is 5% larger than just the pure measurement error, because that 5% error is attributed to possible systematic. So it has to be under 5% based on our analysis.
These numbers include those?
These numbers include those. All of the cosmology interpretation include the systematic error already. And the key is that systematic error is small. The component is very small, like 5%.
Okay, I don't see any further questions. Let's thank you. Last one.
I just wanted to comment on Rajesh's question. That's the way to get redshifts, right? Through radio imaging, interferometry is easy enough, but you need it in 3-dimensional space. So that's how redshifts are easiest because of the emission lines.
Yeah, the redshifts
will also infrared and everything. Yeah.
Redshifts are easiest in optical.
Okay, so let's thank Shadab for this very nice colloquium.